Welcome back to the Deep Dive. Today, we are tackling something that, honestly, it sounds more like science fiction than engineering. We're talking about perfect time.
Or as close to perfect as we can possibly imagine. A listener sent over some amazing sources on the atomic clock, and our mission today is to really unpack it.
Right. Not just how it works, but why this incredible precision
Yeah.
is, I guess, the invisible glue holding our modern world together.
Exactly. It's absolutely non-negotiable for so much of what we do.
So let's just jump right in with the mind-bending number. Because we're not talking about a watch losing a few seconds a day.
No, not even close.
The statistic from the sources is, get this, the most advanced atomic clocks are so accurate they'd lose maybe 1 second every 15 billion years.
And that's the number you have to anchor on. I mean, to put that into perspective, you have to think about the age of the universe itself.
Which is what, about 13.8 billion years, right?
Around there, yeah. So this clock's accuracy, its potential, literally exceeds the entire history of time as we know it.
That is just staggering.
It is. And it tells you right away that the mechanism can't be anything we'd recognize in a normal clock. No gears, no springs, no pendulums.
Sure, because all that stuff wears down. It's affected by temperature, by gravity, by, everything.
Precisely. Those are all flawed human-scale systems. They will always eventually drift out of time.
Okay, so if it's not mechanical, what is it? What is the actual engine inside an atomic clock that's doing the counting?
It's counting something fundamental in the laws of physics. It's called atomic oscillation. Basically, the constant, super regular vibration of an atom.
So you're not measuring a pendulum swinging.
No, you're measuring something like an electron jumping between energy levels inside the atom itself. It's a natural, unchangeable frequency.
We've basically outsourced timekeeping from our own engineering to matter itself. What kind of atoms are we talking about here?
The gold standard for decades has been the cesium-133 atom. And the story there is actually fascinating. Back in 1967, the world needed to redefine what a second actually was.
They needed a universal standard.
A perfect reproducible standard. And they landed on cesium because it has this incredibly stable transition frequency. It just doesn't change.
How stable are we talking? What's the number?
Okay, the official definition of 1 second is the time it takes for a cesium-133 atom to oscillate exactly 9,192,631,770 times.
9 billion times per second.
Per second. That number is now the bedrock of our global time standard, UTC. It's like having a metronome that clicks over 9 billion times a second and never, ever misses a beat.
I mean, how do you even count that? How do you measure something happening that fast without, disturbing it?
Now, that's the real technical genius of it, because you're right, it's not enough for the atom to vibrate perfectly. You have to observe it perfectly.
I'm picturing trying to hold a single atom still, which sounds impossible.
Well, it's harder than that because if the atoms are moving around, you get the Doppler effect, which changes the frequency you observe. So you have to basically stop them.
Stop them.
Almost. They use a technique called laser cooling. They fire these incredibly precise lasers at the cesium atoms, which slows them down until they're barely moving, just a fraction of a degree above absolute zero.
You're freezing atoms in place with light just to watch them vibrate.
Exactly. And then you also have to shield them from literally everything. Magnetic fields, radiation, anything that could interfere. It's all done in this perfectly controlled vacuum.
Wow. So that achievement is almost as incredible as the atom stability itself.
Yeah.
But I have seen some talk about newer optical clocks. Are we already moving beyond cesium?
We are, yeah. Cesium is amazing, but it's kind of reaching its theoretical limit. These new optical clocks use different atoms, like strontium, and they vibrate at much, much higher frequencies.
Hundreds of trillions of times a second, I think I read.
That's right. And the higher the frequency, the more ticks you can count in a second, which means you can slice up time into even finer intervals.
So a finer ruler gives you a more precise measurement.
A much more precise measurement. The newest optical clocks might only lose 1 second in, say, 30 billion years. It's a constant push for a better definition of the second.
Which brings us to the big question, right? Why? If my phone is a second off, I'm still on time for a meeting. Where does this level of hyperaccuracy become, well, critical infrastructure?
The biggest one, the one that affects you every single day, is GPS satellite navigation.
Which we all just take for granted.
Yeah.
How does the time on a satellite connect to where I am on a map?
The whole system is just a giant clock, really. Your phone figures out how far it is from a satellite by measuring the time it took for a signal to travel from there to you.
And since we know the speed of light,
Which is constant, right? So time equals distance. But the signal travels so fast that the timing has to be perfect.
what happens if it's not?
As the source is laid out, if a satellite's clock is off by just 1 billionth of a second, a nanosecond, your location is off by about 30 centimeters, a foot.
1 nanosecond.
Now imagine it's off by a bit more. Suddenly, your GPS is telling you you're in the next lane over, or even tens of meters away from where you actually are.
The whole system would be useless.
Yeah.
I mean, self-driving cars, airplanes landing in fog, precision farming, all of it just fails.
Total chaos. And this is where the really wild part comes in, the detail that goes beyond the basic explanation.
Okay.
The clocks on the satellites don't just have to be accurate, they have to be constantly corrected for the laws of physics, for relativity.
You mean Einstein's theories of relativity?
The very same. The satellites are moving incredibly fast, so special relativity says their clocks should tick a little slower than ours.
Right.
But they're also in a weaker gravitational field way up in orbit, so general relativity says their clocks should tick a little faster.
Wait, you're kidding. So the engineers who built the GPS system actually had to do the math for relativity just so I can find the nearest Starbucks.
They absolutely had to. If they didn't, the combined effect would make the satellite clocks gain about 38 microseconds every single day.
And what does 38 microseconds mean in terms of location?
It means your position would be off by about 10 kilometers. And that error would grow by 10 more kilometers every single day.
So after a week, it would think I'm in another country.
Pretty much. The whole system only works because we are constantly adjusting for the fact that time itself is warped by speed and gravity.
That's just, it's incredible. But GPS can't be the only thing. Where else is this flawless timing essential?
Think about the global financial market. Algorithmic trading, where billions of dollars are exchanged in milliseconds.
Okay, I see. Everything is happening so fast.
So fast that you need to know the exact sequence of events. If two trading firms are out of sync by even a few microseconds, one of them could get an unfair advantage.
So it's about fairness. It's about creating a level playing field globally.
Exactly. Regulators now mandate it. You need that atomic clock standard to prove who clicked buy first, down to a fraction of a millisecond.
And you mentioned infrastructure as well.
The power grid. This is a huge one. Our electrical grids run on alternating current, AC, that has to be perfectly synchronized, usually at 50 or 60 cycles per second.
What happens if they fall out of sync?
If one power plant starts to drift even slightly from another, you create massive instability in the whole system. You risk cascading failures.
Blackouts.
Huge blackouts. So atomic clocks are used to make sure every generator in the grid is pushing and pulling in perfect synchronized harmony. Your lights stay on because of the flawless vibration of a cesium atom.
It's really amazing when you connect the dots. We've gone from this abstract, impossible, number 1 second in 15 billion years, all the way to my car's navigation, my bank account, and the lights in my house.
The entire networked world runs on the atom's perfect schedule, and that brings up a more philosophical point that the sources hinted at.
Go on.
This perfect, flawless, absolute precision, it only exists in nature, in the fundamental laws of physics, in the atoms themselves. It's not something humans can actually create.
That's a fascinating thought. We can build these incredibly complex systems, but for the most fundamental measurement of all time, we have to borrow perfection from the universe.
We just harness it. We build our fallible, complex human systems, our satellites and stock markets, on top of a standard of perfection that is completely external to us.
Our entire global infrastructure rests on something we didn't invent but just discovered.
Our stability is literally based on the stability of an atom.
So here's something to think about. What does it mean that all of our most advanced human technology relies on a standard of perfection we ourselves can never achieve? The next time your GPS guides you perfectly to your destination, just remember that your position in the world is guaranteed by the vibration of an atom that has been ticking flawlessly since before the Earth even existed.